Hello everyone, in this tutorial video I'd like to explain how alternating series work, as well as how they are specialized/specific functions. An alternating series is given its name because it can be written as -1 raised to the power of n times b subscript n, where b subscript n is a different infinite sum, or -1 to the power of n plus 1 times b subscript n. It is important to note we can use the properties of exponents to rewrite series that do not look exactly like this to get them to do so. For example, -1 to the power of n plus 2 may not look like any of the two functions provided above, but we can rewrite it as -1 to the power of n times -1 to the power of 2, because of how exponents work. Unfortunately for us, -1 to the power of 2 is -1 times -1 equals 1. In conclusion, this series simplifies to -1 to the power of n, which we do have as one of our tools in the alternating series definition. By similar reasoning, if we have n minus 1 as the exponent, we write this as -1 to the power of n plus 1 times -1 to the power of -2, because of something plus 1 minus 2 is something minus 1. In conclusion, we can see that -1 to the power of n minus 1 equals -1 to the power of n plus 1 upon simplification, which may not seem to make much sense at first, but if you remember how -1 works when you multiply it, it makes more sense. With that out of the way, we can state that if we have a sub n as an alternating series in either of the two definitions, and b sub n must be greater than or equal to 0, for all terms n in the series, then it follows if the limit of b subscript n approaches infinity and equals 0, and we know b subscript n is strictly decreasing for all values n, then it follows we have definite proof that the series a sub n is convergent, because of the fact we have a power of -1 times the limit of 0, which is 0. With that out of the way, if we are asked to test if this limit is convergent or divergent, we would do this by rewriting this as -1 to the power of n plus 1 times 1 over n to get it in the format specified by the definition of the alternating series, taking the limit of 1 over n as it is our b subscript n, which as n approaches infinity, 1 over n approaches 0, and we next test if it is strictly decreasing, which we can see is true because 1 over n is always greater than 1 over n plus 1, because of the fact the denominator is smaller, the lower you are in the hierarchy of the sum. In conclusion, since we have proven the conditions for it to be convergent, the limit is convergent. We can test a limit like this by choosing our b of n to be n squared over n squared plus 5. But unfortunately, from how limits work, the problem with this is that the limit equals 1 and not 0. So we see the infinite series of -1 to the power of n times anything besides strictly 0 will have a constantly changing value, so we cannot state that it converges to anything. However, this is only true for this test, but we remember that there are other types of tests to see if it converges or diverges. So just because one test fails, we cannot automatically assume that it diverges. In particular, we can take the limit as n approaches infinity of the function, which is not the same thing as the infinite sum. But unfortunately, the same problem arises, in that -1 keeps changing values, even though the rest of the function approaches a finite value. In conclusion, since we cannot definitely state a finite limit of one part that it converges to, using this test either, it follows that we now have definite evidence that the series must diverge. Sometimes you will have to be creative in recognizing alternating series, such as this example, by noticing that cosine of n times pi can be rewritten as -1 to the power of n, because of the fact cosine of pi is a known value of -1, and -1 times itself n times is by definition -1 to the power of n. We get this in the alternating series form by seeing that b must equal 1 over square root of n. We take the limit of b of n as n approaches infinity, which is 0, and seeing that, because each term in the sum of b and m is lesser than the previous term because the denominator is greater, it follows we have definite evidence that the series is convergent. Now that we have seen how to test alternating series specifically, we can discuss what absolute convergence is before we move on to applying that as well as alternating series in the ratio and root tests. Don't forget to subscribe if you found this video informative, and make sure to see the other tutorial videos, and follow me on either Facebook or Twitter for more content.